Everyone, today I'm going to solve indeterminate beam problem by using moment distribution method. The method in and itself is a very powerful method to solve the indeterminate problem, but today I'm going to solve a simple beam problem, twist span beam. The roller and the hinge support at the outside, and a roller support at the interior, inside. So let me draw the beam. Okay, so this is my beam, so I'll make it twist span. So this is 25 feet, let's say this is 15 feet. Okay, and this is, we have a uniformly distributed load of 3 kg per foot, and we have the, let's say this is 2I moment of inertia, and this is I. It seems a little complex, right? But just to expand. So first of all, what I need to do is we just have to identify, like, what will be the deflected shape of this beam. So let's say here the moment is 0, is a hinge, so it cannot take any moment. So as a roller support, the moment at the end is 0. So let me quickly make a sketch and show you. Okay, so this, okay, so it will let's say when we put the uniformly distributed load from top, it will try to deflect this way, go this way, deflect 0. There's no, so there's a rotation here, so and then this so we have fixing moment here. No, we don't have fixing moment here. Okay, so we have the fixing moment here because when we put the load, the beam try to rotate and try to deflect this way. So in order to prevent that, we have the end moment, the support moment, fixing moment. Try to overcome this, so this support will be act like a fixed support. And when you go further to solve this problem, you can refer to I would say there are dozens of references where you can find the fixing moment, where one end is fixed and the other end is a roller or hinge support. So here in this case we have a uniformly distributed load over here. So the fixed end moment, let me say this is point B, point C. So fixed end moment of BA is equals to WL square over 8. So WL square over 8. So our sign convention is clockwise is positive and counterclockwise is negative. So here when we put a load, when we put a load on this beam, so this try to deflect this way, so we have a fix and moment which tries to overcome this deflected shape this way. So this is clockwise and this is on the other side, it's anti-clockwise. So this is positive and this is negative moment. So that's why fixed end moment of BA is positive, it's going clockwise. So that will be our W is 3 kg per feet. WL square, what is our length? It's 25 feet square over 8, which gives us 234.375 kg feet. Again, for the fixing moment for span BC is equals to, it will be minus WL square over 8. So the minus W square over 8, this will be sorry, now we have a different length here. This is 15 feet, so it's minus 3 kg per feet times 15 feet square over 8, which gives us minus 84.375 cubic feet. Okay, so now the next step is to find the distribution factor. So how you're gonna find the distribution factor? So at the roller support, so the distribution factor is calculated as distribution factor of joint AB is equals to the stiffness of member AB to the sum of the stiffnesses. So here in this case, always when you have a the exterior roller or hinge, the fix and moment is the distribution factor is always 1, because stiffness of member AV by the stiffnesses of member connected to this joint is AV, so it will be 1. So the distribution factor of AB is equals to 1, distribution factor of CB is equals to 1, so we have to find the distribution factor of BA and BC. So let's find the distribution factor of BA, which will be stiffness of member BA to the stiffnesses of the member connected to the joint B, stiffnesses of member BA plus stiffnesses of member BC. From here the stiffness, so when the far end is pin or roller, then our stiffnesses will be 3EI over L. So 3E and our I is 2I over L, the length is 25 feet, over by, so 3E 2I over L plus BC. So what is the stiffness? Is the same, right? 3 EI, we have only I over L, it's 15 feet. So calculating this, we will get our distribution factor as 0.54, and distribution factor of BC is equals to stiffnesses of member BC divided by sum of the stiffnesses of member BC plus BA, which gives me a BC same as 3I over L, right, divided by 3EI over L plus 3EI over L, 25 feet, which gives me 0.46. all right, so we are halfway now. We have our distribution factor, we have our fixed end moment. So we will now make a table. I don't know, let me make a simple table here. All right. Okay, so let's say this is my joint. First of all, joint A, right? We have joint A, we have joint B, and joint C. Boom. So now member AB, so we have here two member BAN, BC and CB. So remember, just keep in mind that let me first write the distribution factor, and I will get back to that point what I'm trying to say. So distribution factor is 1, okay, BA is 0.54 and 0.46. so now let me write the fixed end moment 0, there is no moment at support 0. BA, what's the fixed end moment of BA? It's 234.375, and the other one is BC is minus 84.375. so now as I would say, now you have to set in your mind that where is the moment distributed, where is the moment going to be distributed. So from here the moment from AB will go to the member from moment from AB will go to the member BA, and moment from CB will go to the member BC. That's how it will distribute. So from AB it will go to BA, and from CB from this it will go to this way. Okay, CB goes to BC, from CB goes to BC. That's how we will distribute our moment. So all right, so now what is our distributed moment? Let me lock this joint, draw table. So now how do you calculate the, so is there any moment here? There's no any moment. So the moment we have at joint B of 234.375 and minus 84.375. so this, what is our unbalanced moment? So in order to find the unbalanced moment, it will be negative always 234.375 minus 84.375. so this is our unbalanced moment. Okay, so this is our unbalanced moment. So we have to distribute this unbalanced moment based on the distribution factor. So distribution factor is 0.84. So let me quickly, okay, so let me do this. Okay, so let me minus 234.375 minus 84.375. so this is going to be minus 100, and this whole thing will gonna be minus 150, and we will distribute this in 0.54, 0.46. I'm just creating these things to make you easy to understand. So mine 0.54 is minus 81 and minus 69. Okay, so that's the unbalanced moment here. So it's minus 81 and minus 69. Sorry, it looks last point. Okay, minus 69. so then where is the moment going to go now? Can you carry over this moment to this side? No, it won't go. Can you carry over to this side? No, it won't go. It's done. So the moment is distributed now. That's it. You cannot go to the further step from here. So then just summation of moment 0 153.375 minus 153.375 and 0. That's all. I'm sorry, undo. Oh my god, erase. Let me erase this and make it little. So that's our moment. So then let me erase this also, the unbalance is true. Now, so once you find the moment, then you can break down the structure, and this is our support, right? So just check. So we have, what we have is, we have the loading, that's 3 kip per foot. Same here. Okay, so I would say this is reaction at A, V at B, so this will come here, okay, this is reaction at C, B at BBC, BBA, so this is reaction at B. RB is equals to VBA plus VBC. So now let's put our moment. So this is clockwise, right? 5. So we have clockwise. So we have clockwise moment of 153.375, and we have anti-clockwise moment right here. It's 153.375. So putting all those, we create a free body diagram, and we'll try to find out what's the reaction at A, what's the reaction at B, and reaction at C. We already got our moment. So let's take a section AB, this little piece of section. Okay, we call it reaction at A. We call this shear at VVA, 3 kip per foot, clockwise 153.375. Give it, let me give a unit to this one. This is moment. Give it. We will do summation of moment at A = 0, clockwise. This point is A, which is a little right to support A. We just got this section and try to find the internal forces. So 3 kip per feet times, I believe this is 25 feet, times 25 feet times 20 feet by 2 plus 153.375 kip feet minus VBA times 25 feet equals to 0. So from here I got my VV is equals to 43.635 kips, and if you do summation Fy equals to 0, then RA plus VVA minus 3 times 25, from here you will get RA is equals to 31.065 kips. So that's our reactions. Again, take another support, this support, that's this member, I'm sorry, as this is support, it's member BC with a length of 15 feet, boom, and then we have a load of 3 kip per feet. Okay, what else do we have? We have a moment of same 153.375 kip feet. This is B, this is C. Let's do summation moment at C equals to 0, and from here we can find VBC times 15 feet minus 3 times 15 times 15 divided by 2, that's just 25, and minus 153.375 equals to 0. Therefore VV is equals to 32.725 kips. If you do summation of Fy 0, then you will get RC equals to 275 kips. Okay, so our main calculation, the moment at internal support B is calculated, it's 153.375. Just we're trying to find out the reactions, and we'll plot the shear force and bending moment diagram. Alright, so we got our reaction forces. Reaction forces at A is equals to 31.065 or 365. I think it's 365. Just 31.365 kips. Boom. Okay, so now, okay, so this is our A, this is support B, this is support C. What's our reaction force? It's positive, so it will go up 31.365 kips, and it will, so because of 3 kip per feet of UDR, it will push 3 kip per every feet, so we will get kind of like this. It's too much, so I'd say, and this equals to what was 43.365 kips. How you get this? It's 31.365 minus 3 times 25, which gives us minus 43.635 kips. And reaction at B 32, right? Here reaction at B is, it's positive 32.725, so it will try to push up. Hold on, our reaction at B is at hasn't calculated, we haven't calculated yet. So reaction at B is equals to, look here, this the shear force, internal shear force, this BVA is positive, is going off, right? So if we cut a section here, in order to balance this, we have to put the downward the downward forces of VVA. That's going to be, this is VVA, that's going to be 43.635, so it will act downward. And also from here VVC is positive, so on this support it will be, it at the just right to the support, it will be downward. So in order to balance, so RV has to be upward, so that's going to be RV is equals to VBA plus VBC. That's going to be 5 kips plus BBC, this is BBC 32.725 kips, which comes out to be 76.36 kips. So now you have minus 43.365 plus 76.36, it will go up by 32. Kips, again you will push by 3 kip per feet, 3 kip per every foot, so it will go minus 3 times 15, it's 12, boom, and reaction at C is 12.75. Did you miss anything? Okay, this is 12.275 and this is 12.275 kips. So this is our shear force diagram. So from here you will be able to calculate the bending moment diagram. In order to find that, you need to find this distance, you need to find this distance x, so area of this, area of this, area of this, area of this will give you the, so our assumption is that upward positive, this is our positive shear and this is our positive moment and positive. Okay, let's go ahead and calculate the bending moment diagram also. So we'll say, let me take this small little piece, let me make a triangle, okay, here. So we'll take a small triangle and this one, the one with the blue one, the bigger one, and we'll calculate the distance x. So it will be 31.365 divided by x is equals to 43.365 kip plus 31.365 kip divided by total is 25. So we get a value of x is equals to 10.455. Let me solve it. 31.365 of x is equals to 43.365 plus 31.365 divided by 25. That come out to be 10.49 or 10.49, 10.49. So 10.49, 10.49, 49. It's wrong. So x is that. Okay, let me calculate, go ahead and calculate the other distance too. So if I wanted to find that, so let me make this big triangle and this small triangle. So that will be 32.995 divided by x equals to 275 kips plus 32.995 kips divided by total 15. This came out to be x is equals to, let me solve, 32.995 divided by alpha x equals to, I'm using Casio 115 ES 0.995 divided by 15. This come out to be 10.93 feet. This is the distance in feet. So let's go ahead and compute this area. My god, no place to write in, so let me, okay, so this little area is gonna be half base, it's 10.49 times the height is 31.365. It is, that's gonna be 164.5. This is positive. Everything that's above this horizontal line is positive, below that is negative. So this area was gonna be half time base is gonna be 25 minus 10.49 times the height is gonna be 43.365. So this is going to be 314.61. This little piece area is going to be half times 10 point times height is 32.995, 180.3. maybe we round off something, some digit more, looks like, but anyway, so let's the main thing here is to learn the concept. So just learn the concept and you can do it by yourself. So 24.7. So why am I computing this area? This area is equals to the moment. Okay, I'm trying to draw the bending moment diagram. So in order to draw the bending moment diagram, so you need to calculate the area under the shear force is equals to bending moment diagrams. So A, B, C. Okay, now before we start, so how is your curve gonna go? Okay, so this is linear, so we have our bending moment diagram as parabolic distribution. So look at the slope is highest at point A and it's decreasing. Then what we can do is we try to, the moment here is 0, so the slope is maximum here, hence the slope is maximum, the curve will go this way, maximum, and it's 0. Okay, so it's decreasing, increasing, or it's like maximum here and it's decreasing, and it will be 0 here. So that moment is equals to 164.51 kp. And from here, what's the slope? What's this? It is increasing, right? Slope is increasing. So it's 0 there and it's increasing. Slope is 0 here and it's increasing. Sorry. let me draw nice. I think I drew a little, sorry. Slope is decreasing, maximum decreasing 164, and from here the slope is increasing to this point B. So this is support B, and from here what's the value? So 164.51 minus 314.61. look at the shear diagram. 150, something we the reason that we did not came up with the correct value, we round off some values somewhere, we made calculations maybe a little, so it will come exactly. So we have to check the calculation, but just so this, try to solve by yourself and let me know. It will be this value will come out to be, it's not 164. let me rewrite this again. So this one we made a little rounding error there in our calculation. So 163.46, so this is moment is going to be 317.375. this moment is going to be 178.49, and this moment is going to be this area is going to be 25.1125, something like this over here. So 163.46 minus 317.375, so this moment will be 153.915, it's negative, and from here it will rise up plus 178.49, so it will go, because slope is decreasing, 24.575 give it, and finally minus 25.1125. it will close up to 0 point something, but it will close up to 0 if you do it correctly. So here I'm just giving you the concept how to draw and how to calculate the fixed end moment, calculate the support, the moment at the support, interior support. So this is our 46, this is a positive, negative, positive, 0 moment, support B, this is support A, support B roller support, support C roller support, and this is our bending moment diagram, BMD. Yes, that's all I have. Thank you for watching, and please do remember that whenever you do the carryover of the moment, just know where the moment will be carried over from which end to which end. Here at joint A it cannot take any moment, so the moment from BA does not come to member AB, and at joint, same with joint C, cannot take any moment, so moment from BC won't come to member CB. Just keep in mind, and always try to draw the arrow where the moment is transferring. In this way it'll be easy for you to do the carryover moment. Here we have a simple span beam, so we step doesn't allow us to go further than this. We computed our moment, but remember this is a very important problem. So this problems and appear to be I think it appeared in one of the exam. So there is an exam. I don't say which exam is that, but this is really important for if you're preparing for any structural exam, FEP, whatever. So just alright, thank you so much for watching. If you want me to solve any other indeterminate problems, then let me know or send me an email. I'll just put the comments below, and I'll try to bring it up your problem with the solution. So with that being said, I'll just try to say thank you for watching. Thank you for watching the video. Thank you for watching the video, and yes, try to solve like the similar types of the problems where you will be able to do it correctly. Thank you. Bye bye.